Assalamualaikum to all panelists. My name is Mohammad Haikal Firdaus bin Jota, and today I will present to you my FYP1 proposal of the title Prediction of Railpad Fatigue Failure using Finite Element Analysis. During my study, the work is supervised by Dr. Abdul Malik bin Abdul Wahab. The slide is divided into three parts. Part 1 is the introduction, which contains project background, problem statement, research objective, scope of study, and research limitation. Part 2 is the literature review, which contains fatigue analysis, finite element analysis, and fatigue life prediction. Part 3 is the methodology, which contains study methodology, and lastly, expected result. On the research background, the research focused on the railpad and the elastomer. From the picture, you can see that the railpad is a circled one, and it is sandwiched between the steel rail at the top and the sleeper at the bottom. The railpad is used to protect the sleeper from wearing and impact mitigated from the passing train, and it is made out of rubber to dampen the shock and vibration. It also comes in various elastomer types and stiffnesses, where study shows that low stiffness and high stiffness railpad has their own pros and cons. For the low stiffness railpad, it possesses high impact attenuation that reduces damage on lower elements and the transmission of noise and vibration, but it causes large rail deflection and lateral displacement, which increases the chance of derailment and reduces the pad's lifespan. On the other hand, the high stiffness railpad reduces the displacement of rail and energy consumption to operate the railway, and also increases the pad's lifespan. But it also increases the load transfer to the sleeper, which can damage it and the elements below it. Because of that, the balancing of railpad stiffness is very important for the safety of the railway operation. For the elastomer, it is also widely known as rubber and comes as synthetic or natural rubber. Also, it has a lattice non-linear characteristic that causes the fatigue analysis method for metal not applicable for the material. Or in simple terms, if we divided the railpad into sections, the characteristic of the first section will not be the same for the next section, and so on. On the problem statement, the problem of the study is that there is no study on the fatigue life of railpad, despite many research on the fatigue life of elastomer has been carried out. Also, the effect of variables such as frequency, temperature, tow load, and amplitude onto the fatigue life of elastomer studies were not being considered. Because of that, the objective of the study is to develop a 3D FEM model to analyze the fatigue life of railpad, also to investigate the fatigue life of railpad under the influence of frequency, temperature, tow load, and amplitude of the railway. For the scope and limitation, the study will only focus on the Green-Lagrange strain and the Ogden strain energy density model to predict the fatigue life of railpad. Other than that, only 3 types of railpad elastomers will be studied for this project. Also, only the listed variables below will be considered for the study, which are the temperature, frequency, tow load, and amplitude. For the literature review, the first part is the fatigue analysis. The fatigue analysis of elastomer has been conducted through experimental and numerical approach. Examples are given on the tables, where the analysis is applied onto the engine mounts and the automobile cradle mounts. The method used for each analysis were different from one another. For example, Chung uses material properties of octane hyperelastic material and CXH fatigue coefficient for the fatigue life prediction of the engine mount. Towhead, on the other hand, uses Marlowe model to characterize the cradle mount's rubber and predict the crack initiation life of the cradle mount using the maximum principal strain. And lastly, Kim uses Ogden strain energy to characterize the engine's mount's rubber, and also maximum Green-Lagrange strain and maximum Ogden strain energy density to create the crack depletion formula and predict the fatigue life of the engine mount. For this study, I will use the research done by Kim to carry out the fatigue analysis of the railpad. Next is the finite element analysis. It is essential to characterize the material properties of hyperelastic material, or in other words, elastomer, from its stress and strain relationship. This can be defined from the strain energy potential, for example, Ogden strain energy. This model needs three sets of test data from the elastomer, which are the uniaxial tension test, shear test, and biaxial tension test. After that, we can use the FEM software to calculate the maximum Ogden strain energy density and maximum grain-local strain of the elastomer and the components for the next step. And the last part is the fatigue life prediction. The fatigue life of elastomer is predicted through the crack inflation formula, where we will use the maximum grain-local strain and the maximum Ogden strain energy density of the elastomer to formulate the crack inflation formula. After that, the crack inflation formula will be used to predict the fatigue life of the rubber components using the maximum grain-local strain and the maximum Ogden strain energy density of the components calculated from the FEA analysis previously. The methodology of the study is as shown in the diagram, where the first step is to do a literature review. During this step, the mechanical properties of the steel rail and concrete slipper should be defined. Also, the uniaxial tension test, shear test, and biaxial tension test of the elastomer will be retrieved from the literature collected. After that, the next step is to do the model of the rail pad characteristic. During this process, the modeling will be done via FEM using MSc March software. I will be using the Ogden strain energy potential to characterize the elastomer using the experimental data collected previously. After that, the next step is to validate the model with the experimental result. During this step, I will have to redefine the model if I found that the FEM result generated from the MSc March did not satisfy the experimental result. Also, these steps should satisfy the objective one of my study, which is to create the FEM of the fatigue analysis of rail pad. After that, the next step is to do the fatigue life analysis, where in this step, the damage parameter, maximum grain crunch strain, and maximum Ogden strain energy density of the elastomer and rail pad can be calculated via FEM software. Also, via crack nucleation formula, I should be able to calculate the fatigue life of rail pad using the damage parameter collected. Also, the temperature, frequency, tail load, and amplitude will be considered during this study. This process should satisfy the objective 2 of my study, which is to analyze the effect of temperature, amplitude, frequency, and tail load onto the fatigue life of the rail pad. After all of the steps is completed, I can proceed to write the report of the study, and after that, the study is completed. On the expected result, the study should allow me to calculate the fatigue life of rail pad corresponding to the maximum grain crunch strain and maximum Ogden strain energy density calculated from the FEM software. Also, the study should allow me to visualize the effect of temperature, frequency, tail load, and amplitude onto the fatigue life of rail pad, where from the literature review, it shows that this variable should reduce the fatigue life of the rail pad. And that will be the end of my presentation. If the panelists have any question regarding my study, you can get in touch with me using the email address given or the phone number on the slide. That is all from me. Thank you.